The Big Bang is not the beginning of the universe. Wait, don't we usually say that the universe began at the Big Bang? Well, you can often hear something like that, but the problem is, that's not entirely true. I'm not saying that the Big Bang theory is wrong, but there are quite a few myths and misconceptions associated with it. Perhaps one of the main misunderstandings is what the term Big Bang actually refers to. Which specific moment and which events are meant. Many people think that the Big Bang theory describes the birth of the universe, but in my video about alternatives to the Big Bang, I've already said that this is not the case. The Big Bang describes not the birth, but the evolution of the universe, what happened to it from the early moments of its existence, but not from the very first moment. So, does this mean something existed and was happening before what is generally referred to as the Big Bang? It seems like it, and we even have some ideas about it. And I'm not talking about the singularity, which also raises questions. Here's one example. You've probably heard that the cosmological singularity refers to a state where the entire universe was compressed into a single point. But here's the question. Isn't it now generally believed that the universe is most likely infinite? How then can infinity be compressed into a single point? An infinite-sized point? What? Today let's try to find the answer to this question, as well as to the question of what existed before the Big Bang, and what is even really meant by that. What are some of the problems with the Big Bang, and how does cosmological inflation help solve them? We'll talk about all this and more, and my name is Andrei, and this is Cosmos Elementary. Let's first discuss the concept of cosmic inflation, a brief period in the universe's history when it drastically expanded in a very short moment. Just like with the Big Bang, inflation can be confusing. One reason is that different sources can present seemingly contradictory statements. For instance, Wikipedia states that cosmic inflation is a phase of accelerated expansion just after the Big Bang. Many of you have probably seen various versions of images like this one, with different annotations or none at all. But here it's clearly marked, first the Big Bang, and then inflation, and then everything else. However, here's a snippet from a book stating that inflation occurred before the Big Bang. And here's another article, for example, and another one. There are quite a few of them. So was it before or after Big Bang? Seems like quite an important detail. Here the issue lies in the details and what exactly is meant by the Big Bang in this context. But let's go through everything step by step. I've talked about the Big Bang theory several times, so let's quickly review the key points. In 1950, Albert Einstein published his general theory of relativity. This allowed for discussions about the structure of space-time and the evolution of the universe in terms of specific physical laws. In 1917, Einstein applied his theory to describe the entire universe and suddenly found that his results contradicted the prevailing, at that time, belief that the universe was static. His solutions indicated that the universe must be either expanding or contracting. Einstein didn't like this, and introduced a cosmological constant into his equations to allow for a static universe. However, as some of you probably know, he later got rid of this constant. But it found a way to make a comeback. In 1922, Alexander Friedmann solved Einstein's equations and found that the universe could be homogeneous, isotropic, and most importantly, not static. Unlike Einstein, he wasn't afraid of these results. His solutions described three possible types of the universe, each with its own shape or geometry and corresponding evolution: a closed universe, an open universe, and a flat universe. He was one of the first, if not the first, to suggest in this context that the universe might have a beginning. In 1927, Georges Lemaitre also described an expanding universe and later introduced the concept of a primeval atom, from which the universe emerged. This is what we today call the cosmological singularity. It eventually became known as the Big Bang theory. A term coined in 1949 by Fred Hoyle, interestingly an opponent of the expanding universe. Despite Edwin Hubble's discovery in 1929 of the universe's expansion, observed not only through theoretical calculations but by seeing galaxies receding from us, and the fact that the farther away the galaxies were, the faster they were receding. In addition to the observed expansion of the universe, there are two other main pillars on which the Big Bang theory initially rested: primordial nucleosynthesis and the cosmic microwave background radiation. All theories suggested that all chemical elements were formed either in the interiors of stars or during supernova explosions. However, the problem was that predictions about the quantities of various elements in the universe of those theories did not align well with observations. Georgy Gamow and his colleagues developed a theory that light elements, such as helium and few other isotopes, could have formed in the early universe when it cooled, in the moments following what we call the beginning. Their theory predicted that 25% of the matter in the universe should be in the form of helium. This explanation is consistent with the hot, dense state of the early universe described by the hot Big Bang theory. And most importantly, it aligns with modern observations. We indeed observe this distribution of ordinary matter as predicted by primordial nucleosynthesis. And of course, there is the cosmic microwave background radiation. If the universe was dense and hot, then there should be residual radiation evenly distributed throughout the universe from that period. This radiation would have been able to propagate freely once the universe expanded and cooled sufficiently. This radiation was predicted in 1948 by Robert Herman, Ralph Alpher, and once again Georgy Gamow. In 1965, it was discovered by Arno Panzias and Robert Woodrow Wilson. The temperature and properties of the radiation turned out to be very close to what was predicted. All of this, along with other data and observations over time, established the Big Bang theory as the primary model for the evolution of the universe. Frequent misconceptions probably arise for many due to the term Big Bang, and also because of animations like this one, which I myself use sometimes. Looking at them, one might indeed get the impression that there was a point in the center of the, explosion, and that everything is flying outward from it. This leads people to questions like, where is the center of the explosion and the universe now? But such animations are certainly not an accurate scientific representation of what is meant by the Big Bang. It's like with the images of the solar system. To fit all of the planets on one image, you have to sacrifice scale and draw in correct proportions of distances and sometimes even sizes. These images and animations give us a general understanding of the structure of the solar system, but they certainly cannot be used for calculating spacecraft trajectories. Similarly, these animations illustrate the fact of the universe's expansion, but they are imprecise and sometimes even incorrect. Another point I mentioned earlier is the issue of singularity and the infinity of the universe. The singularity is indeed a real problem, much like in the case of black holes. Whenever singularities, here regions of infinite density, appear in calculations, it likely indicates that there's something we don't fully understand. If we imagine that we rewind time, everything in the universe gets closer together. And we can reach a singularity where everything is compressed into a single point. But at this point, the familiar laws of physics stop working, and they cannot describe what actually happens with this singularity. But in brief popular explanations of the Big Bang theory, the singularity is almost always mentioned. So, how can you compress an infinite universe into a point? In fact, this question can be rephrased in a more conservative way. We don't even need to reach a singularity. We can stop at a very small size. The question remains valid. How can infinity be made small? In other words, how can something infinite change in size? When we talk about an expanding universe, it is more accurate to discuss not how its size changes, but how the distance between two objects like galaxies changes. This animation demonstrates that, but again only in a two-dimensional closed analogy. This change in distance is described by a parameter known as the scale factor. By the way, the scale factor is a very important parameter in Friedmann's equations. This parameter is dimensionless, meaning that it doesn't have units like meters. At the present time, with the age of the universe being approximately 13.8 billion years and the radius of the observable universe about 46.5 billion light years, the scale factor is assigned a value of 1. The farther back in time, the smaller this parameter becomes. For example, here's a cosmological calculator that allows you to roughly estimate what the universe was like at different values of the scale factor. You can also adjust the Hubble constant, whose measurements currently vary somewhat, but we'll leave it as it is. At a scale factor of 1, the age is approximately 13.8 billion years, i.e. the current age of the universe. The distance to the particle horizon, or the radius of the current observable universe, is about 47 billion light years. With a slight adjustment to the Hubble constant, it will be even closer to 46.5 billion light years. In general, this represents modern-day universe. At a scale factor of 0.5, the age is already 5.8 billion years, and the horizon is at 18 billion light years. At a scale factor of 0.1, it's only 4% of the current universe's age, and so on. I'll leave a link to the calculator so you can play around with it yourself. So what does all this tell us? The entire universe might be infinite. The farther we look into the past, the smaller the distance between 2 points becomes, and the denser the matter is concentrated. Talking about size, whether it becomes smaller or larger, can be applied to the part of the universe we call the observable universe, a section of the universe limited by the particle horizon, beyond which we fundamentally cannot observe. But beyond the horizon, the universe likely continues. It's quite possible that the universe extends in a similar way with the same properties, physical laws, galaxies, stars, and so on. If the universe were finite with a boundary, it would be somewhat easier to imagine how everything in the universe could collapse into a single point. However, in the case of an infinite universe, discussing a point becomes more challenging. It's more plausible to assume that the universe was already infinite, just with everything closer together and denser. There wasn't a single point or a center of the explosion. It's not to say that the concept of infinity is much easier to grasp, but at least discussing the evolution of the scale factor is more accurate than talking about the size of the entire universe. And if you really want to talk about size, you should specify the observable universe. But if before the expansion described by the Big Bang Theory, the universe was already infinite, then what was there? Inflation can help us address this question. Despite the Big Bang Theory's success in describing the evolution of the universe within certain timeframes, it has serious problems. In the video about alternatives to the Big Bang Theory, I mainly listed these problems. Now let's delve into them. Typically, there are three main issues: the horizon problem, the flatness problem, and the monopole problem. And inflation can serve as a solution to all three problems. So, what is the horizon problem? As I've said before, we are located at the center of the observable universe, within a sort of a bubble with a finite radius, bounded by the particle horizon. This is all the universe that we can see. This is due to two factors: the limitation of the speed of light and the finite age of the universe. Since the moment light started to travel freely through the universe, it had only a certain amount of time to reach us. And the most distant radiation we can detect is actually the cosmic microwave background radiation. You can imagine that we are at the center of a sphere. On the inner surface of this sphere, we observe the cosmic microwave background radiation. This surface is called the surface of last scattering. One interesting aspect of this is that we can observe regions of the universe where hypothetical observers in those regions cannot see each other. Here we are at the center of our observable universe. Here is the horizon, or the boundary of the observable universe surrounding us. As I mentioned, the universe is likely larger, and beyond our horizon it continues. But if an observer were in a different location, they would have their own horizon. If an observer were at our horizon, we would be at the edge of their universe or at their horizon. If we place two observers at opposite ends of our observable universe, let's call them observer A and observer B, we can see both of them, but they cannot see each other. Each has their own horizon. And since the universe hasn't existed long enough for light from this observer to reach this one, these two regions of the universe could not have exchanged information or influenced each other. At the same time, modern measurements of the CMB show that it is very homogeneous across the entire universe. Even though maps of the cosmic microwave background radiation look colorful, these temperature fluctuations across the sky are actually very, very small. Modern measurements of the temperature of the cosmic microwave background radiation tell us that it is approximately 2.73 Kelvin across the sky, or to be more precise, about 2.7255 Kelvin. The temperature fluctuations shown in different colors represent changes of roughly 100,000th of this temperature. By the way, if you have questions about how radiation can have a temperature, I discussed that in a separate video and I'll leave a link to it. In general, the CMB is very, very homogeneous across the universe. So what's the problem? The same temperature everywhere indicates thermal equilibrium. It means that at the time the cosmic microwave background radiation was emitted, in the very early universe, it was already in thermal equilibrium. But typically, for a volume of matter to reach thermal equilibrium, different parts of that matter need to interact with each other. For example, if we take two containers, one with hot gas and the other with cold gas, and open a valve between them, the gases will mix and reach thermal equilibrium when the temperature becomes uniform throughout the entire volume. But we already established that we observe regions of the universe that could not have interacted with each other. How then did the universe achieve thermal equilibrium? Why do we see such homogeneous cosmic microwave background radiation? How do distant regions of the universe know about each other's properties without any possibility of interacting? This is the horizon problem. It's unclear how the universe could have reached equilibrium given the lack of communication between these regions. One could attribute it to initial conditions, simply assuming that the universe was that way from the beginning. While this might be an answer, it's not very satisfying. Just like with the fine-tuning problem of the universe, about which I have a separate video, the approach of simply saying that's just the way it is and accepting it does not provide us with any deeper understanding of the structure of the universe and its evolution. Next, we have the problem of the flat universe. This also reminds of the fine-tuning problem of the universe. The geometry of space-time in the universe and critical density are one of the most pressing issues in fine-tuning. In brief, the fine-tuning of the universe refers to the situation where it appears that our universe is seemingly set up perfectly for the existence of structures like stars and galaxies and life itself. It seems that the considerable list of parameters in the universe with values that specifically allow for the existence of both structure and life cannot simply be a matter of chance. And why do we talk about the flatness problem in the context of the Big Bang? This problem is big enough on its own, but the Big Bang makes it even worse. Let me remind you that depending on the total amount of matter in the universe, its fate and shape could vary. Recall the parameter known as critical density. It is this critical density that is considered to be equal to 1. If there is too much matter, meaning the density is greater than 1, the universe could have a closed geometry and might collapse back on itself after expanding for some time. On the other hand, if there is too little matter, meaning the density is less than 1, the universe would have an open geometry, and at some values of critical density, it could even expand so rapidly that no structures would form to begin with. But there's also a middle option when the density is exactly 1. There is just enough matter in the universe so that it does not collapse back, but also does not expand too quickly. This is a very simplified explanation. Well, and modern measurements show that the density of the universe, if not exactly equal to the critical density, is very close to it. And the geometry of the universe is flat. It is often said that the universe is balancing on a knife's edge, and people are surprised by the very low probability that the universe would randomly end up with exactly the right density value, right in the middle, from a vast range of possible values. But why is this a problem specifically for the Big Bang theory? In theory, flat geometry and density equal to the critical value is an unstable spatial situation. And if it is close to or equal to the critical density now, it should have been that way in earlier epochs of the universe as well. Even small fluctuations could lead to very significant changes in the universe, and in the early stages of its evolution, this problem becomes even more severe. For us to observe the universe as we do today, the density in the early moments of the universe should not have deviated from the critical value by more than a factor of 10 to the power of -64. Just a tiny deviation by such an incredibly small fraction, and the universe would be different. It's not surprising to think the fine-tuning of the universe here. Again, one could simply accept it as a given and conclude that we are just very lucky, which some people do. However, others believe that such a coincidence must have an explanation. And finally, the problem of monopoles. Today we know of four forces, or more precisely, fundamental interactions that govern the universe: gravity, electromagnetism, the strong interaction, and the weak interaction. According to the logic of the Big Bang theory, in the earliest moments of the universe, when it was very dense and hot, all four interactions could have been initially unified into one. Then, as the universe expanded and cooled, a series of phase transitions occurred, during which these interactions eventually separated. This all happened very quickly, on scales of unimaginably small fractions of a second. One of the main consequences of these phase transitions, as described by modern theories, is that topological defects should arise in the very fabric of space-time. Monopoles, strings, domain walls, textures, we won't go into details here right now. The main point is that in theory, we should observe these defects, but so far we haven't seen any. In general, the classical Big Bang theory that existed until 1980s could not explain all these problems. Therefore, it needed an extension in the form of inflation. It does not cancel the Big Bang theory, but rather complements it, and also helps to resolve these problems. For almost the entire duration of its existence, the universe has been expanding. And there were different stages. For the first few billion years, the rate of expansion was slowing down, and then the expansion began to accelerate again, which we now attribute to dark energy, but that's another story. If we try to describe inflation in the simplest terms, it is an era when the universe didn't just expand, but expanded like crazy. It expanded exponentially. It doubled in size, or more precisely, the distance between two hypothetical points doubled, every unimaginably small fraction of a second. And after 10 to the power of -33 seconds, which is 1/1000th trillionth of a second, a very tiny fraction of a second, the universe expanded by a factor of 10 to the power of 30th, or by a factor of 1,000 billion times. After that, the expansion slowed down, and so to speak entering a normal expansion mode, as described by the hot Big Bang theory. The idea of inflation was proposed in 1981 by Alan Guth. In his original description, before the beginning of the universe's expansion, the universe was in a state of false vacuum. This state is metastable, meaning it can remain in this state for a long time, but there's also a chance of a spontaneous transition to a true vacuum. And I have a separate video on false vacuum as well. So a phase transition to a true vacuum state occurred, leading to exponential expansion. Here we could make a simple analogy with supercooled water. You can cool water to a temperature below its freezing point, but if it's free of impurities and remains undisturbed, it can stay liquid. However, if it is disturbed, even a tiny nucleation point is enough, and the entire volume of supercooled water quickly turns into ice. Similarly, the universe before the Big Bang was in a false vacuum state. As a result, for example of a random quantum tunneling event, a microscopic region of true vacuum formed, which rapidly expanded and eventually became our universe. But this idea had problems. For example, there wasn't a proper mechanism for exiting the inflationary state, and such a universe could produce many of these bubbles, which would collide with each other, leading to inhomogeneity in the observable universe, and this is not what we observe. But this version is known as old inflation. These shortcomings became clear fairly quickly, and by 1982, Andre Linde, Paul Steinhardt, and Andreas Albrecht proposed a version known as new inflation. We won't dive into too much details, but in short, the difference with new inflation is that the phase transition to true vacuum here is of second order rather than first. And the transition, or rolling into the true vacuum, is slow. By the way, this is the screenshot from a lecture by Alan Guth himself, where he compares new and old inflation. I'll leave a link to it in the description. The main point is that this version required less fine-tuning and allowed for inflation to end. You might have a valid question: where did all this occur? It is proposed that before the emergence of our universe, there existed a hypothetical inflaton field. Today, the universe is quite successfully described by the quantum field theory, according to which fields permeate the entire universe, and at each point in space and time, these fields have certain values. And all particles, electrons, photons, quarks, they're not just little balls of matter, but disturbances in these fields. And the inflaton field is the field responsible for inflation. This hypothetical field is scalar, meaning each point in the field is described by just a single number. An example of such a field in physics is the famous Higgs field. And there were even ideas that the Higgs field might be the very inflaton field, but that's a matter of debate. Scientists didn't stop at new inflation either, because it had its own problems. Just a little later, in 1983, Andre Linde again proposed the idea of chaotic inflation, which did not require initial conditions of thermal equilibrium and where chaotic conditions naturally led to inflation. Today there are many inflationary models, but overall it is considered an integral extension of the Big Bang theory. Not least because it helps to solve a number of problems I mentioned earlier. First, the horizon problem. How it is that we see the cosmic microwave background radiation suggesting that the universe was initially in thermal equilibrium with almost the same temperature everywhere. Inflation allows us to avoid the need for such fine-tuned initial conditions. It permits a scenario in which the universe was not initially in thermal equilibrium. Remember that I mentioned that during inflation, the scalar factor of the distance between 2 points in space had to increase by orders of magnitude in a brief moment. If you calculate how quickly this happened, it turns out to be much faster than the speed of light. We might start to worry, since special relativity prohibits faster than light motion. However, we need to remember that it prohibits this for objects moving through space-time, but it fully permits the expansion of the space-time itself faster than light. But doesn't the horizon problem arise due to the limitation of the speed of light? Before inflation, within the existing particle horizon, there could have been regions not in equilibrium. Here is a region in equilibrium, and next to it, a region with different properties. However, inflation happened so quickly that the particle horizon, which by definition is tied to the speed of light, could not keep up with it. Space-time itself expanded so rapidly that all inhomogeneities moved beyond the horizon, and only a region in thermal equilibrium remained inside. This is what we observe in the cosmic microwave background radiation. So there is no need for the entire universe to have been in thermal equilibrium initially, and this explains why we still observe it. This also allows, after inflation stops, for the inhomogeneities to come back within the horizon as it catches up with them. And the small inhomogeneities that we still observe in the cosmic microwave background radiation are explained by quantum fluctuations that were stretched during inflation. Ultimately, these fluctuations led to density and homogeneities in matter and the formation of structures in the universe, such as stars, galaxies, and galaxy clusters that we observe today. As for the flatness problem, the situation is somewhat similar. Inflation does not require the entire universe to have been very close to flat. Very rapid expansion during inflation could have stretched space so much that within our observable universe, there is a region indistinguishable from flat geometry. It's like zooming into a circle so much that the curvature becomes imperceptible, and a segment of it will appear as a straight line. Or like how the Earth appears to be flat. Similarly with topological defects like monopoles. We do not observe them not because they are absent, but because the incredibly rapid expansion during inflation pushed all existing defects beyond the horizon. They exist, but are simply beyond our observational reach. In general, inflation addresses several problems of the Big Bang theory while not negating its successes. If by the Big Bang we mean the history of the normal expansion of the universe from the moment when the observable universe was smaller, everything was closer, density was high, and the universe was hotter, then if we don't rewind all the way back to the Singularity, where our physical laws break down anyway, we can say that before the Big Bang, there was an inflationary epoch. And it turns out that such diagrams, where it shows that there was Big Bang first and then inflation, are incorrect. Here, annotations are more accurate. This diagram simply shows the chronology of the Big Bang. Inflation is more likely what initiated what we describe as the hot Big Bang. What was before inflation? Well, naturally we don't know for sure. I briefly touched on it when discussing the inflaton field and the false vacuum state. There is a hypothesis of eternal inflation, according to which inflation never really ends. Or to be more precise, it does end, but only in certain regions of the inflaton field. And those regions become universes just like ours. And then there could be an infinite number of such universes as well. According to Max Tegmart's classification, this is a level 2 multiverse. Of course, there are many nuances to all of this. And as I mentioned, there are quite a few inflationary models. Again, no one asserts with absolute certainty that everything happened exactly as described in one of the theories. Nevertheless, today the Big Bang theory, along with inflation, is the best and most widely accepted description of the universe's evolution. It even attempts to look beyond what we are used to calling the beginning of the universe. Although it does not provide the final answer to the question of the origin of everything. Yes, we can go another step below the beginning of our observable universe and consider the possibility of eternal inflation. But where did it come from? Was there anything before it? We don't know. And it's not certain that we will ever find out. However, just 100 years ago, we couldn't imagine how deep we would be able to look into the universe. So who knows what will be possible in the future. Thanks for watching. Links to all of the sources are as always down below in the description, and if you enjoyed the video, leave a like, comment and subscribe for more videos in future.